Heat transfer by Jordan, Corey, Neil, and Dane. In thermodynamics, we learn that energy can be transferred between a system and its surroundings. Thermodynamics deals with the end states of processes during which interactions occur, and also with the net amounts of energy transfer by heat and work for the processes. Heat transfer is energy in transit due to a temperature difference. Whether there is a temperature difference in a medium or between media, heat transfer will occur. We refer to the different types of heat transfer processes as modes, which are conduction, convection, and radiation, as demonstrated in the illustration below. Conduction is heat transfer across a stationary medium with solids or liquids. It happens on a molecular and atomic scale. If one end of a metal rod is at a higher temperature, then energy will be transferred down the rod toward the colder end because the higher speed particles will collide with the slower ones, with a net transfer of energy to the slower ones, heating up the cooler end of the rod. Convection is heat transfer by motion of a fluid, such as in air or water, when the heated fluid is moving away from the source of heat, carrying energy with it. Convection above a hot surface occurs because hot air expands, becomes less dense, and rises. An example of convection is the steam bubbles rising from the bottom of boiling water to the top, bringing energy with it. Thermal radiation is energy transfer by the emission of electromagnetic waves which carry energy away from the emitting light. Thermal radiation occurs through a vacuum or any transparent medium, a solid or a fluid. Fourier's law is the concept that heat can only transfer from warmer objects to cooler ones. It also explains the rate of conduction heat change. Newton's law of cooling tells us that the rate of change is proportional to the temperature of an object and the ambient temperature. An example of this is cooling down a bowl of soup or a hot drink.
Now that we have completed our basic presentation on heat transfer, we can attempt a practice problem. In our practice problem, we're going to attempt to find the rate of heat loss and the daily cost of maintaining a surface at a certain temperature. So our problem states that a concrete slab of a basement floor is 11 meters long, 8 meters wide, and 20 centimeters thick. During winter, the top of the slab is held at a constant temperature of 17 degrees Celsius by a furnace that burns natural gas. The bottom of the slab is underground and remains at 10 degrees Celsius. So we are asked to find the rate of heat loss through the slab, given that the thermal conductivity is 1.4, and we are asked to use Fourier's law, which is Q equals negative Ka dt over dx. Now this can be expanded out to K times dt over dx times the area over the thickness of the slab. So we know that Q equals 1.4 because that is our thermal conductivity. We multiply that by 17 degrees Celsius, since that's our temperature change. And now we need to multiply it by the area over the thickness. The area would be length times width in this case, and that value would be squared. This value comes out to be 88 meters squared, because I've already calculated for our purposes. And we divide it by our thickness, which in this case is 0.2 meters. You have to keep in mind that the 20 centimeters needs to be converted into meters in order to do this. So that gives us a Q value of 4.312 kilowatts. Now we have to move on to part B. Part B tells us that if natural gas is 1 cent per megajoule, what's the daily cost of maintaining the top surface at 17 degrees Celsius? Remembering that 1 watt is equal to 1 joule per second. So first we have to do dimensional analysis in order to figure out the amount of seconds that that this thing needs to be maintained at that temperature. So we take 1 day, multiply it by 24 hours in 1 day, times 60 minutes per each hour, times 60 seconds per 1 minute, giving us a total of 86,400 seconds. Now we also take our value that we determined in the last part, 4.312 kilowatts, and we need to convert it into joules per second. And in joules per second, it would just be 4.312 joules per second, because 1 watt is equal to 1 joule per second. So now that we have that, we have to multiply our time, 86,400 seconds, sorry, 86,400 seconds, by our energy unit, which is 4.312 joules per second, giving us 3.725 megajoules per day. Now we take that value and multiply that by 0.01 cents per megajoule times our thermal efficiency, which is up here, which ends up being 10 over 9, giving us an answer of 4.14 cents a day in order to maintain this concrete slab at our given temperature. Now I'm going to utilize a butane torch and a couple pieces of currency to demonstrate heat transfer. As we've stated, there are 3 basic ways in which heat is transferred. It's transferred by convection, which something carries heat from one place to another, such as the torch carrying the butane flame, which transfers heat into the penny. Another way to transfer heat is by conduction, which is occurring here as the penny melts. The copper on the outside is conducting its heat to the zinc on the inside, which melts. And there's also radiation, as some of the heat escapes and radiates out into the atmosphere. In this situation, we switch from a penny into a nickel. A nickel is solid steel, so you can see the radiation a lot better, as unlike the penny, it won't melt. It'll just turn red hot. And when we dip it into the water, you can see again, conduction. The heat transfers directly back into the water, as opposed to red hot when it's radiating heat into the atmosphere.